Hello. Welcome to the ZOS Communication Server Technical Update, ZOS V2R5 edition. Both of us are architects for ZOS Communication Server, and as you might guess by the last part of the title, the focus of this presentation will be on new features and function in the ZOS V2R5 version of Communication Server, which became available just a couple of months ago. On the agenda chart, you can see a list of the topics we'll be discussing. With that said, I'll go ahead and move on to the first topic. And that first topic is ZOS Encryption Readiness Technology. ZERT was initially shipped in ZOS V2R3, so by this point in time, many, and maybe most of you have heard of ZERT. Hopefully some of you are using it already. We'll start our ZERT discussion with a couple of background charts. I know that for many of you this will just be a review, but I do think we should start with a level set of why ZERT is so valuable. ZOS provides four mechanisms to cryptographically protect TCP traffic. The first one we'll look at is TLS-SSL direct usage. This is a case where an application directly writes to the System SSL or Java Secure Socket Extension APIs. Those applications provide their own configuration capabilities and their own auditing mechanisms. The second path on the chart, and one that we in Communication Server are particularly fond of, is Application Transparent TLS, or ATTLS. And this is a mechanism we provided well over a decade ago that basically provides a wrapper around System SSL within our stack. With ATTLS, we invoke the System SSL APIs on behalf of the application. You use our Network Configuration Assistant to configure policy for the applications you want to protect and with what security attributes. That policy is installed in the stack, and we call the System SSL APIs on behalf of the application. We support auditing through SMF-119 records, so we have the advantage of a common auditing mechanism and a common configuration mechanism. A third path is virtual private networks using IPsec. IPsec protects traffic at the COM server IP layer. So any application above the COM server IP layer can be protected by IPsec, and of course that's pretty much every application. Whereas paths 1 and 2 are TLS and therefore TCP-only mechanisms, IPsec protects TCP traffic and non-TCP traffic. So this includes UDP. Why is that important? Well, a very important use case for UDP is Enterprise Extender. Many of your organizations still have a significant amount of SNA application traffic and use EE to transport your SNA traffic over an IP network. And the way to protect EE traffic is via IPsec. The fourth and final path we see on this page is Secure Shell using ZOS OpenSSH. OpenSSH is another TCP-based mechanism and provides several capabilities, with probably the most popular being SFTP. OpenSSH provides its own configuration mechanism and its own auditing mechanisms. Now, as we look at this chart with these four different paths, we might ask ourselves, which of these paths are typically in use in your shop, or in the typical customer shop for that matter? Well, the answer is probably more than one of them, and in some cases maybe all four of them. If you have Java applications, you're probably using path number 1 with JSSE. Hopefully many of you are using ATTLS for many of your TLS protected applications, so that's path number 2. Many of your shops use Enterprise Extender, and if you're protecting that traffic, and hopefully you are, you're using path 3. And lastly, some shops have a mandate for secure file transfer through SFTP, and if you have that mandate, you'll be using path 4. So it's entirely possible that you could be using all four paths on this page, so that's indeed a lot of complexity. So given the amount of complexity there is with all those mechanisms, all those configuration methods, and all those auditing mechanisms, how confident are you that all the traffic is protected at the levels you intended and that your corporation mandates? That the right protocols are being used, at the right protocol versions, with the right cryptographic algorithms, and so forth. And if you think there's traffic that's not compliant, how do you figure out who owns the traffic and follow up with them? And it's a moving target because as new applications roll out, how do you ensure those new applications are adhering to the policies as well? And even if you're confident that you are adhering to all the policies, do you have the auditing methods in place to prove this to your manager, to your auditors, and to anyone else that needs to know? This is where ZOS Encryption Readiness Technology, or ZERT, comes into play. The initial deliverable of ZERT was shipped back in ZOS V2R3 and has been augmented with additional capability along the way. ZERT provides two different flavors of SMF-119 records. a subtype 11 record known as a ZERT connection detail record, and a subtype 12 record known as a ZERT summary record. When enabled, there will be at least one ZERT connection detail record provided for every TCP and EE connection, allowing you to understand the complete cryptographic protection history for each of your TCP and EE connections. This is a powerful capability, but can result in a high volume of SMF data. For that reason, we added a capability known as ZERT aggregation, which introduced ZERT summary records. ZERT summary records describe the repeated use of security sessions over time. With aggregation, we write a ZERT summary record at the end of each recording interval for every security session active during that interval. This can greatly reduce the volume of SMF data while still providing a substantial level of cryptographic detail. So while all these SMF records are great, what do you do with them? How do you analyze them and really understand your security posture? Well, you're really going to need a tool to consume those SMF records and allow you to generate reports based on that data. Many of the vendor products out there today, including some IBM products, stepped up to the plate and very quickly updated their tools to consume ZERT summary and/or connection detail records and provide various views and reports of that data. We wanted to provide our own tool to help you understand the ZERT data, and the tool we provide is something called the ZERT Network Analyzer, or ZNA. ZNA is a web-based UI to consume the ZERT summary records and allow you to create queries that will query that data and generate reports. So for example, you could write a query that says, show me all the connections I have that are unprotected or that are protected by TLS but a level less than TLS 1.2. Creating such queries provides an easy way to get a report identifying areas where you might be out of compliance with your security goals. In ZOS V2R5, the ZERT journey continues with a capability called policy-based enforcement, as you see identified in the bottom right puzzle piece of the ZERT picture. This is a new technology implemented through the Network Configuration Assistant and our policy agent. Using the Configuration Assistant, you create rules, and those rules have conditions that describe traffic along with acceptable or unacceptable protection attributes. As ZERT is monitoring your cryptographic information, it detects traffic that matches rule conditions you're looking for, and then can take action based on associated defined rule actions. This diagram provides an overview of how ZERT policy-based enforcement works. At the top left, we see an administrator using the Network Configuration Assistant to create rules, traffic conditions, and associated actions that will be taken when we match those conditions. The rules are then installed into the stack by the policy agent, and then when a TCP connection matches the conditions of the ZERT rule, we take the associated action for the rule. That action could be to permit the connection, write a message to syslog, or write a message to the console. The action could be to write out a single connection detail SMF record for further analysis. In especially serious cases, you might even want to have an action to terminate the connection for significant violations of your security policy. So here's a quick summary of what we've talked about in this section. In previous phases of the ZERT journey, we introduced ZERT discovery, ZERT aggregation, and the ZERT network analyzer. ZERT policy-based enforcement is introduced in ZOS V2R5, and it now provides a way to go beyond just collecting this data and monitoring it and maybe using ZNA to generate reports. Now you can actually take actions based on the cryptographic attributes of your TCP traffic. Lastly, here's a ZERT reference chart that describes policy-based enforcement at a very high level, provides a set of quotes from customers about ZERT and how important they think it is, and lastly, and maybe most importantly on this chart, is the link in the bottom box. This is a link to a Things You Should Know About ZERT page, sort of an all-in-one, one-stop shopping page with lots of links to various things about ZERT, videos, documents, and so forth. So if you're interested in ZERT, please bookmark that page and keep it close at hand. Our next topic will be IPsec certificate reporting enhancements. If you'll recall, IPsec was path 3 in our background information chart for ZERT. With IPsec, you're using something called the Internet Key Exchange Protocol to negotiate security associations between the IKE peers. During a Phase 1 IKE tunnel negotiation, security association information is exchanged, and you see a list of that information on this chart. But what we're going to focus on here is certificates, because problems with certificates can be particularly difficult to debug. The IPsec-K display command can be used to display IKE tunnels, and you can get quite a bit of useful information from that command, but it does not provide a lot of help for identifying which certificates were used as part of the Phase 1 negotiation. In ZEOS V2R5, the IPsec-K display is updated to display additional information about local and remote certificates. We provide the expiration date, the serial number, the issuer and subject distinguished names, as well as the lengths of those names. In addition to providing that information through the display output, we also provide it through SMF records, type 119, subtype 73 and 74, and also through an NMI. This next chart shows an example output of an IPsec-K display command. This may be a little bit difficult to see as you look at the screen right now, but if you'll download the PDF associated with this webinar, it's probably going to be easier for you to see this that way. What you can probably see even on the screen right now is that about the bottom third of this display output is in boldface. And that's all the new information that was added in V2R5 that gives you the expiration information, the serial number, and the distinguished names and links of those names. So this can be very useful in debugging certificate-related problems. Continuing in a similar vein, V2R5 also introduced ATTLS and IPsec certificate diagnostics. We'll look at ATTLS first. ATTLS negotiation failures are reported with EZD-1286I and EZD-1287I messages. You see an example of the 1286 message, and there's quite a bit of useful information there as far as helping you identify the actual connection involved. And very importantly, in red, you see a return code. You can look up that return code to help you understand why the negotiation failed. That's all well and good, but if the negotiation failure is due to an issue with the peer certificate or the certificate chain, our customers have told us that often the return code is not sufficient, and they typically have to collect system SSL trace data to complete the investigation. In ZEOS V2R5, System SSL added a new PI that communication server exploits, allowing us to provide new messages to provide additional diagnostic capability. So, when enabled, you can get a number of new messages. For example, looking at the EZD-2052I message you see under the first sub-bullet, you see a lot of useful information, including the return code, the Certificate Management Services return code, and a System SSL provided description text string that gives you a little more information. There's also information about the distinguished names and the serial number, as well as the certificate source and the trusted source that's used to validate the certificate. If you go to a slightly higher level of diagnostics, you'll get the 2053 and 2054 messages, and these are where you really get useful information about the chain that was used for the validation. There will be a 2053 message issued for every certificate in the chain, and if you look at the sample output here, you see this says certificate 1 of 3. That will be followed by one that says certificate 2 of 3, then 3 of 3. You'll notice it says failing cert equal no, but 3 messages will say failing cert equal yes, and that's going to tell you which of the certificates in the chain was causing the problem. Lastly, the 2054 will be issued, and that provides information on the data source that is used for the validation of the peer certificate. Next, we have IPsec certificate diagnostics. With IPsec, NSSD or ICD will exploit System SSL Certificate Management Services for certificate validation. If there's a failure, and the failure is due to a peer certificate or certificate chain issue, the return code or CMS error code may not be sufficient for your diagnostic effort. In V2R5, ComServer exploits that same new System SSL API to provide new messages with additional diagnostic data to help you diagnose certificate-related failures. Once again, you do have to enable this using the existing IKE syslog level statement within the IKD configuration file. As with the previous item we discussed, the goal here is to reduce the need for collecting System SSL trace data. When enabled, you will now get this new EZD-2055I message, which will give you additional information on the failing certificate. As you can see by looking at the sample, the 2055 message gives you information like a return code, the reason code, a description of the problem, the distinguished names, the serial number, and your certificate source, as well as the trusted source that was used to validate the certificate. If you've also enabled the debug SA level of messages, you'll get a certificate diagnostic details message for every certificate in the chain, and one of those messages will indicate failing cert equal yes, so that you know which certificate actually caused the problem. Additionally, you'll get a certificate diagnostics data sources message with information on the data sources used for the failed validation of the peer certificate. And with that, I'm going to turn this over to my colleague who's going to talk to you about Shared Memory Communications version 2.
shared memory communications over remote direct memory access, or SMC-R, is a protocol solution that is based on sockets over RDMA. SMC-R enables TCP sockets applications to transparently use RDMA, which provides direct, low-latency, peer-to-peer communications. Communicating peers, that is TCP/IP stacks, dynamically learn about the shared memory capability by using traditional TCP/IP connection establishment flows, which I will show on the next chart, thus enabling the TCP/IP stacks to switch from TCP network flows to more optimized direct memory access flows that use RDMA. RDMA is available on standard Ethernet-based networks by using the standard referred to as RDMA over Converged Ethernet, or ROCE. ROCE enables the use of standard TCP/IP and RDMA solutions such as SMC-R over the same physical LAN fabric. The network interface is typically referred to as an RDMA network interface card, or RNIC. So how does z/OS Communication Server enable transparent use of RDMA? The client and server applications continue to use existing TCP sockets programming to create a connection by performing the three-way handshake. As part of this handshake, a TCP option indicating whether the local peer is SMC-R capable is also passed. When one peer that supports SMC-R detects that a remote TCP/IP connection partner also supports shared memory communications, the connection is transparently and dynamically switched to use SMC-R protocols. That means all reading and writing of data occur using RDMA operations. The beauty of this technology is that the applications are unaware of the use of shared memory for their communications. Now obviously, because of the additional inline negotiation for SMC-R that occurs over the existing TCP connection, SMC-R makes sense to use only for persistent or long-lived connections, or for connections that stream data such as FTP file transfers. For short-lived connections, the extra SMC-R flows needed might not provide much overall benefit. Shared memory communications was extended to also support memory-to-memory communication between peers on different LPARs on the same IBM Z server. Shared memory communications direct memory access, or SMC-D, uses internal shared memory for communication between two SMC-capable peers that are located on the same CPC. So, network communication can occur without the need for network interfaces, I/O slots, or other network resources like switches or routers. Similar to SMC-R communication, SMC-D negotiation occurs by first establishing a three-way TCP handshake with remote peer. During the handshake, a TCP option indicating SMC-D capability as well as same CPC colocation are used to transition the connection to SMC-D. But instead of needing RNICs to transfer data, internal memory that is shared between the LPARs is used to read and write the data. You may be asking yourself, what about hypersockets for LPAR to LPAR communication? Well, one of the drawbacks of hypersockets is that general-purpose CPs are used to move the data between LPARs. For non-persistent, short-lived connections, the CPU overhead is minimal for the hypersockets and will perform better than short-lived connections using SMC-D due to the additional network flows to negotiate the RDMA connection. But if you need to stream a lot of data between the LPARs, then this is where SMC-D shines, both in reduced network latency and CPU savings. With the initial versions of SMC-R and SMC-D, one of the rules that has limited the general use cases is that traffic using SMC is not routable. Both peers need to be on the same layer 2 network. Because they follow the same SMC protocol and rules, Both SMC-R and SMC-D require a single subnet. If the peers are on different subnets, this will be detected prior to RDMA negotiation, and the connection will remain as a TCP-based connection. IBM previously issued a statement of direction for SMC version 2 that extends the benefits of SMC to additional workloads and use cases by lifting the single subnet limitation for both SMC-R and SMC-D. Support for SMC-D V2 was made generally available on Z15 and V2R5 of ZOS last year via APAR's PH22695 and OA 59152. It allows peer-to-peer communication within an IBM Z system when the peers reside in different subnets. SMC-Rv2 was made generally available as part of the V2R5 GA on Z15. This support, also known as routable RoCE, allows peer-to-peer communication across different ZOS systems that traverse one or more network routers. So, returning to our original diagram for SMC-R, you can now see that SMC-Rv2 allows communication between peers residing in different subnets. SMC-Rv2 encapsulates the data flowing between the peers into UDP packets, allowing them to be routed. It uses UDP port 4791, so if you have any firewalls configured between the two peers, they must be reconfigured to allow this port to pass through. Likewise, for SMC-D, you are no longer limited to communicating with peers residing on the same CPC only if the peers belong in the same subnet. There is no router needed between the peers, but the two APARs will be able to directly use memory-to-memory communication. So the obvious question is, does SMC-Rv2 provide the same performance benefits that the earlier version of SMC-R did over native TCP sockets, even when being routed through one or more hops? For persistent connection OLTP workloads, network response times are reduced by over 60% versus TCP-based traffic. And for workload streaming data, such as database software replication, network latency is reduced by 45%. And the CPU story is just as good. For these same OLTP workloads, CPU utilization used for networking is reduced by up to 15%, while for streaming workloads, CPU is reduced by even a greater amount, 85%. A similar story can be told for SMC-D V2 versus hypersockets. For long-lived connections for OLTP traffic, network response times are reduced by nearly 50%, while networking CPU usage drops by over 45%. And for those streaming workloads, both network latency and network CPU consumption drop by 90%. So there are really no excuses not to use SMC-D V2 for these types of traffic patterns. To find additional information about SMC V2, there are several resources you can explore. First, there is a presentation out on SlideShare about the SMC V2 technology. There is a white paper available to download that describes the implementation of SMC-D V2. Stay tuned for a future white paper on SMC-Rv2. Don't forget to use the SMC applicability tool to determine whether your existing workload traffic patterns could benefit from using one of the SMC technologies. Next, I'd like to shift gears and talk about enhancements in V2R5 for TCP/IP initialization complete notifications. There are many workload applications that have a dependency on TCP/IP being fully initialized before they are started. But when is TCP/IP really initialized? And that answer may be different depending on what the application needs. When you start TCP/IP, you will see message EZA-IN11I being issued. This looks like it is a pretty good indicator that TCP/IP is initialized. But digging deeper, that message only indicates TCP/IP has completed initialization of base services. Depending on your configuration, there may be a set of extended or optional functions that also need to be completely initialized before your workload applications can be started. For example, do the applications need dynamic VIPAs or Sysplex distributor? Do ATTLS policies need to be loaded because your applications require secure connections? And so on. Your automation may need to process multiple TCP/IP messages to determine when an application can be started. And that list of messages may be different for each of your workloads. So in V2R5, Communication Server simplifies this process by providing a new message to indicate all required network services based on your configuration are initialized. In addition, you can programmatically determine whether TCP/IP has completed initialization by either listening for a new TCP/IP stack up ENF or check for the existence of a system-level name token pair that gets generated once TCP/IP has completed its initialization. The new message, EZD1314I, will now be issued when TCP/IP and all configured extended services, such as Sysplex networking or ATTLS, has completed. Additionally, a new eventual action message, EZD1315E, may be issued if TCP/IP initialization is being delayed because it is waiting for one of the configured extended services to complete. For example, it could be that dynamic VIPA processing has not completed, or TCP/IP is waiting for the policy agent to finish loading its policies, or not all of the IPsec infrastructure is operational yet. Once TCP/IP detects that whatever extended services was delaying initialization has completed, it DOMs the eventual action message and issues EZD1314I. At the bottom of this chart, you'll see an example of TCP/IP starting but waiting for Sysplex processing to complete. As I previously mentioned, you control what extended services TCP/IP should be waiting for before indicating that initialization has completed. There are two new parameters that can be specified on the global config TCP/IP profile statement. One indicates whether to wait for the policy agent to complete its initialization or only wait if ATTLS was configured. The other indicates whether to wait for IPsec infrastructure, including the IKE daemon, has initialized. Note that there is no statement for Sysplex networking initialization because TCP/IP will always wait for that to complete. And now back to you.
The next topic I'd like to talk about is function removals. I know function removals are not exciting, but you do need to be aware of them. There were several functions removed from Communication Server in ZOS V2R5, and you can see a list of them on this chart. All of these removals were announced through statements of direction at least 2 years ago, and for some longer than that, so hopefully there's been plenty of warning. The vast majority of you will not be affected by the first 4 of these. The one that I do want to draw your attention to, because it's the one that might be a little more problematic for some of you, is the last one in the list, the removal of native TLS SSL support from the TM3070 server, FTP server, and the Digital Certificate Access Server, or DCAS. Prior to V2R5, you've been able to configure all 3 of these servers via either native TLS configuration options or via ATTLS. However, beginning in V2R5, all of these must be secured using ATTLS. The native TLS SSL configuration options have been removed. Please be aware of this as you begin planning your upgrade to ZOS V2R5. Also, understand that the FTP client is not included in this change. In V2R5, you can still configure security for the FTP client through either native TLS SSL configuration options or via ATTLS. There are a few additional topics I'd like to talk about, and I'll start with a couple of new statements of direction. Both of these refer to capabilities that will still be supported in V2R5, but will not be supported in the release after 2.5. So please read these and make sure you know whether or not they apply to your configuration. The first SOD we will discuss is the withdrawal of support for link station architecture and LAN channel station, or LSA and LCS devices. This statement of direction was included in the availability announcement for ZOS V2R5 back at the end of July. There's a lot of words in this statement of direction. You can read those words at your leisure, but allow me to summarize. If you have OSA adapters, and all of you do, make sure you know whether you have any chip IDs of type OSE configured. That's OSE. Since the OSE chipped is no longer going to be supported in a future hardware deliverable, the related LSA and LCS devices are no longer going to be supported after ZOS 2.5. I doubt many, if any of you, are using LCS, as it's a very old protocol that's not used much anymore. However, there may be a few of you still using LSA devices. LSA gave you a way to have a native Ethernet capability for SNA. If you have OSE chippeds and LSA devices defined today, before you move to the release after 2.5, you will need to pursue an alternative form of connectivity for your SNA traffic, such as Enterprise Extender or TN3270. Another statement of direction that was issued in that same availability announcement is the removal of OSA device link home configuration support. For many years now, you've been able to configure OSA adapters with device link and home statements. But way back in ZOS V1R4, which is about 20 years ago, we introduced the more modern interface statement, and you've been able to configure OSA adapters using that way as well. Over the years, as we added new functions for OSA, configuration for those functions has always been through the interface statement, not through device link and home. So now we believe that it's time to remove the support for configuring OSA with device link and home and instead require you to use the interface statement. That will be the case in the release following ZOS V2R5. Now note that device link and home statements will continue to exist after 2.5 for some other device types, but not for OSA. Next, I'd like to talk about the new function APAR summary web pages. Hopefully by now you're familiar with these pages, as we've had them for a number of years now. But if you aren't, go to one of the two links on this chart, either the 2.3 page or the 2.4 page, depending on which release you're using right now. Bookmark that page because I think you're going to find it very useful. On these pages, we talk about all the new function APARs that are available. And for each APAR, we include a summary of the function, a link to the APAR, and other valuable information. On this chart, we see an example entry from the 2.4 page, in this case, the entry for inbound workload queuing for ZCX. You'll notice it includes a quick summary of the function being delivered, links to documentation, and information about dependencies and incompatibilities. It's basically one-stop shopping for our continuous deliverables. So find the version of the page that corresponds to the release you have now, bookmark it, and check it occasionally. You may find some really interesting functions that you want to consider exploiting. Many of you are probably interested in the performance characteristics of ZOS Communication Server. With that in mind, a few months after we ship a new release, we typically put out a performance summary report. This report provides quite a bit of information about things like CPU utilization, transaction rates, the cost of encrypting traffic, and other interesting information. The link you see on this chart is to the 2.4 Communication Server Performance Summary Report, which is the most current one we have available right now. You might be thinking, well, this presentation is about 2.5. Where's the 2.5 report? My guess is that the 2.5 report will probably be published sometime in the first quarter or early second quarter of next year. When it's available, we'll announce it on our blog, so keep an eye out for that. Many of our customers are interested in education, including digital badges, and we have several of those now. Two of those, the Networking on ZOS Foundations badge and the ZOS TCP/IP Configuration with NCA badge, have been around for a while now. We more recently added a new one, and that's the ZOS Network Security Foundations badge. With as much interest as there is in network security these days, I think you'll find this a great course to take, so you can proudly display your network security badge. Hopefully you're already following our blog on the IBM community, but if not, please consider doing so. ZOS Communication Server used to have a blog on DeveloperWorks, but that was sunset a couple of years ago and was replaced by the blog in the IBM community. We provide a variety of interesting information through this page. Recent topics have included ZERT and other network security topics, a 2.5 update, share conference information, and even the announcement for this webinar. I mentioned that the coming 2.5 performance summary report a couple of charts back, and when that's available, it will be announced and linked on this page as well. And that's it. I would like to thank you for attending our session.